I almost feel like starting by saying, now for something completely different, because mainly, I've listened to the talks in the first half. We've been talking a lot about various organisms and plants that live in the chalk streams. There's going to be a lot of organisms in this talk as well, but I can assure they're well and truly dead, and have been for some time. So, what makes the chalk in chalk streams? Charlie's right, she pointed out straight away. If anybody says to me chalk is a white, monotonous carbonate rock, I'd probably strike them dead, I think. It's not. I'm going to try and prove to you tonight that it is very variable. And if you can spot the variations, they can be very, very subtle. But if you spot those variations, then it will have an impact on the chalk streams that you're looking at, the flow that you might expect. So bear with me if you think this guy's talking out of a strange orifice somewhere. So, what is this rock we call chalk? Let's start. It's typically white, what we call semi-lithified. It's not terrifically hard. And it gave its name in Latin, Creta, which is chalk, to the Cretaceous period. The Cretaceous period is the period of geological time which lasted from about 144 million years through to 65 million years. So the last chalk that was potentially deposited, and I say potentially deposited, in the UK was about 65 million years ago. So it had quite a long history, but we've also had a huge history subsequently. It also gave possibly gave the Roman name for England, which was Albion, as the Latin for white is alba, and chalk being white, you can imagine that if you were arriving coming northwards from Calais, the first thing you might see is a lot of white cliffs, so therefore it became Albion. Had the Romans been going southwards and seen all the French chalk cliffs, it might have gone the other way, but they weren't. They were coming in our direction. So what's chalk made up of? It is important that we recognise that it's a biogenic rock. And what I mean by that, it's made up of the skeletal remains of various plants and animals. We're looking at a rock that doesn't contain a great deal of what we would call terrigenous or land-derived sediment. It's pure white biogenic limestone. And this is important in terms of how it affects water flow through it. Well, let's just have a go. I'm going to give you a quick rundown. I don't know if is there a pointer, Joe? Have we got a pointer here? No. Most of the fossils that you see around here, things like sea urchins, mollusk shells, sponges, they do contribute to the chalk, but they're not the main part of it. We're going to be looking at a lot of these things over here, and I'm going to explain what those are as we go on. But we do get big fossils. You can see here, this is a large ammonite, thing called Parapozosia. This one's down in Brighton. This one's on the at Thanet. Again, large Parapozosia. These would be anything up to 1 metre across. So we do get big ones. Not very many, but we do find them. But we also get tiny ones as well. And the fossils I want to talk about are what we refer to as the microfossils. And here you can see a particular bug that I work on, a thing called a foraminifera. And yes, you can get them through the eye of a needle. But what we're also looking at predominantly are these things. And these would be, just a tiny little pinprick on the side of that foraminifera. These things are called coccoliths. And coccoliths are what the chalk is made of. All the chalk you're walking over, all your water goes through, it's been filtered through billions and billions of these. And that is an essential feature of chalk. So let's have a look at, you've got the coccoliths. Here we go. I'll talk about these in a little bit more detail in a second. But what they are single-celled plants. They're golden brown algae. The technical name for them is Haptophysia. And these single-celled algae produce plates of calcite, of calcium carbonate, which provide them with, if you like, shelter. It also provides, there are some suggestion that the diffraction of sunlight through the crystalline plates also because they are photosynthetic, helps them to photosynthesize. So they're extremely important. When they break down, we end up with lots of tiny crystals as well. And we get these things, the foraminifera, and as I say, these are the things that I specialize in. But these things are very, very common in the chalk. We sometimes get similar things called radiolaria. These are single-celled organisms. They're made of silica. And because they're made of silica, you can then start saying, oh, perhaps this is where the silica in flint comes from. I could prove you wrong on that, but that's another story. We get mollusks, a lot of mollusk debris. Sea urchin, starfish, echinoderm fragments, they all contribute. We get a lot of bryozoan material. As I say, a lot of all these organisms, we find them in modern day oceans, but in chalk seas they were very common. And we get sponge spicules. And these are silica, and these are sponges which lived on the sea floor. They had skeletons made of silica, which is this stuff, which actually dissolved into the chalk at a very early stage and then subsequently recrystallized to form those flints we were talking about. So these are also a very important constituent, which nowadays you will not find them unless you go looking in the right places. But in fact, they are contributing in a major way to what makes up the chalk that we see. So there we have it. There's a sort of typical chalk cliff. This is one in the Etretat section in northern France, and you can see the white chalk layers, regular layers of flint. But as I say, chalk isn't all the same. You can, if you look at it, you can also see there are some peculiar patterns in the flints down here. Everywhere you go, chalk is different. Listen to me, it really is, I promise. Perhaps a bit closer to home, place you will recognise, top of Beachy Head. And you can see a sort of crowd of geologists who are normally a little bit idiotic by standing too close to the edge. I'm the one in the yellow jacket, and you think, well, you know, he's the prat who's actually closest. But in fact, there was another guy here, even closer. But you can see these regular bands of flint. This is the sort of thing, this is what your normal concept would be about what constitutes a chalk section. I was asked on Saturday why I should be asked at a wedding why you get flint bands and these sort of regularity, but I was. It was late in the evening. So I gave the guy I said, do you want the long version or the short version? He said, we better make it the short version. So I'll give you the short version. The Earth rotates around the Sun, but it doesn't do it in a uniform circular pattern. It does it in an elliptical orbit, so sometimes it's going to be closer to the Sun than at others. And not only that, it's on an oblique axis, and it's also got a bit of a wobble. So if you add all those factors in together, then you're going to get a periodicity, a regularity in how the Earth is relating to its energy supply, the Sun. And I've already told you that the constituents of chalk are all those little plants, all those tiny coccoliths. And obviously, if you've got a massive energy coming from the Sun, they're going to bloom. And when they bloom, you get masses of thick chalk formed, which is what you'd expect. In this particular case, there are going to be times when it's just a little bit cooler, perhaps not quite so good for blooming. It also then, that would allow other organisms, things like crustaceans, lobsters, those sea urchins we saw, to burrow through the chalk, to get established as burrowers. And it's in those burrows where flints are formed. So what you're seeing is a reflection of that change of periodicity while the Earth is rotating around the Sun. Through all that sort of the effectors, the obliquity or the eccentricity, or whatever we want to call, put onto it, we're seeing that cyclicity reflected in flint formation. So, what was unusual about Cretaceous times when the chalk was formed? This is a sort of threefold picture of the various parts of the globe around about 94 million years ago, so at the time when chalk formation was kicking off. That's where we are. This is sort of the Siberian Massif there. You can pick out Africa bit of going across into Asia. An interesting thing, this little bit down here, that's India. India's going to come whacking up through here to form the Himalayas over the Cretaceous period. That doesn't affect us, but it is, it's just so that you know that we can actually monitor these changes that have taken place since this time. But one of the things that, if you look at that, you can see all this pale blue area where sort of Africa would be. Africa was almost 50% covered in what we call an epicontinental sea. It wasn't oceanic, this was raised sea levels that were drowning the land masses. So Europe, up here, was effectively just a few islands scattered across a massive open sea. And that's when I was saying right at the very beginning that we don't see any surface runoff, any terrigenous sediment, the sands, the clays, things like that, coming in to be deposited in our area here, because there's very little land for it to come from. Sea levels are so much higher that basically that land, that hinterland for providing the sediment, has been pushed right back. It's been estimated that if you melted the polar ice caps at both the North and South Pole at the present day, you would raise sea levels by about 125 metres. Okay, this is where you start thinking, I will get my contour map out when I get home and check whether I'm safe. I can assure you, you're not. Certainly not here, you're not. That still doesn't give us enough sea level rise for what we had in the Cretaceous. We're looking at about 200 to 250 metres above present day sea levels. The reason behind that, the ocean basins were changing very, very rapidly. There was a lot of rapid oceanic crust production, and this was forcing, if you like, water levels, sea levels onto the continent. So we also had an incredibly hot greenhouse climate. If you think it's getting warmer now, you should see what it was like in the Cretaceous. I don't know if you go swimming in the North Sea nowadays, you wouldn't recommend it. During the late Cretaceous, we're looking at sea surface temperatures of a minimum of about 23 to 24 degrees centigrade. Okay, in the Atlantic could have been well up onto 35 plus. So we really were talking greenhouse climate. Okay, I've already mentioned we had this major flooding of the continental shelves because of that sea level rise. Less sediment being pumped in. Clear seawater. It had a very low magnesium to calcium ratio, which is important because that facilitates the growth of those coccoliths that I was talking about. So these things, these little single-celled algae, were blooming by the billion in this warm tropical sea on these wide continental shelf epicontinental seas. And we know that we find what we call coccospheres, which are just the fossil remains of the total organism, and those break up to form the individual plates. They disaggregate. And that's what forms chalk. This is going on in the present day, and it's certainly what happened probably, sort of an order of magnitude higher during the Cretaceous. To prove that it's going on in the present day, I think you'll recognise what this is. This is a coccolith bloom off the coast of Cornwall. And you can see this is formed by a single species of coccolith, a thing called Emiliana huxleyi. It's the most common organism on the planet today. Okay, and we're in a glacial period. In the Cretaceous, this thing, the early ancestors of this thing would really have been having a great time. So chalk is initially a coccolith. These are coccoliths breaking down, forming this mass of chalk, and foraminifera. There's a nice little planktonic foram floating around in the sea, breaks down, and that's what your chalk is actually being made up of. So, having proved that, what does it look like in the Chilterns? I was fortunate enough when the A505 Baldock bypass was constructed, I was able to go digging away at the sections as they excavated it. This was the opening of the tunnels. It was a very wet day and the bus broke down, so it was it was a typical English day in the Chilterns, basically. But just to give you some idea, I mentioned that chalk deposition lasted until 65 million years. Well, age is plotted down the side here. If you can't read it, it stops at 83 million years. And in fact, all the chalk that we have in the London Basin, in the Chilterns, is no younger than this red box. The youngest chalk we have, if you wanted the proper name there, is probably low to middle Santonian, around about 85 million years. Any chalk that was deposited, and it almost certainly was, in the last 20 million years of chalk formation, was eroded off before we saw the next sediments deposit on top of it. So what we're looking at in the Chiltern area is really the youngest chalk we get is what we call the Seaford chalk, and you may see these names bandied around. Certainly I'm going to use them now. There's the Lewis nodular chalk and the Newpit chalk. All these names come from Sussex. They were defined by a colleague of mine, Rory Mortimer, back in the 1980s. He was working, he did all his research on the Sussex chalk, and subsequently we've carried that research through into the Chiltern areas, into East Anglia, so that we can actually relate each unit of chalk in this area to what he had right through the North Downs, the South Downs, onto the southern English coast. These are sort of some of the sections that we have in the Chilterns. There's the Baldock bypass, for example, down here, cutting through this sort of Lewis nodular chalk into the Newpit chalk. Now, these formations are defined on changes in the lithology, changes in the character of the chalk. And this is why, as Charlie mentioned, we see variations which we can map. If we can map those variations, we call them formations. And those formations will have an effect on the surface topography and the nature of stream flow and groundwater flow through them. So let's strip off the tunnels. Let's take it back to before the tunnels were put in. So this is the Baldock section as it was being excavated. And we took it right back. There's no tunnels now. You can see a couple of flint bands going through. And in fact, if you may just pick out there are a number of what we call marl seams through there. So what causes them? The first thing I point out in the chalk, these awful looking orange, brown, rusty patches. They don't look very significant. They were actually sponges. Those mark the places where those sponges were living. They often occurred in bands. We can pick them up through here. And all the silica that went into the skeletons of those sponges has gone. It's been dissolved into the sediment. But it ends up forming flints like that. As I say, flint formation, totally different lecture. We'll do that another time. But flints they've formed following fossil burrowing. Okay, now if I show you this, this is a flint, and you can see it's got some sort of structure to it. You can see this structure coming through here. And you say, oh, I don't never see flints like that. But that would have looked like something like this originally, and these are feeding traces of some sort of crustacean. We don't know the actual organism. We refer to the trace, it's a trace fossil that the flint has formed around as a zoophycos, and we get zoophycos flints. If anybody wants, again, you never see flints like that. I've got one in the back of the bag, my bag at the back here. So if you want to see me afterwards, I will show you a zoophycos flint. Try and convince you. We also get these layers, hard grounds. If you look at this, it's not a white chalk. You can see it's got an orangey green tinge to it. This is rich in iron, it's rich in phosphate. It's a natural occurring. This is actually a fossilized sea floor. And you can see that gap going between those two nodules. That's one of the burrows going through it. An animal has burrowed through there between the nodules, and the nodules have been mineralized. And it would have looked something like this with the ammonites, like the ones I showed you at the beginning, only down at this level we call it Lewisicerus. There's a different sort of ammonite. And here are the burrows, and that's where the trace fossils, the crustaceans, were living. There's one of the ammonites that came out of Baldock. This is a big chunk of this thing, Lewisicerus. Just to show you that these rock units can be traced throughout the area. This is Reed Quarry up in northeast Hertfordshire, and just trying to pick out, if you can, although it looks like a monotonous chalk unit through it, there are there's like an orange band there, and if you look carefully, there's another orange band there. That's what we call the top rock. It's the highest of these hard grounds in the area. The local quarrymen used to quarry down to this, and that forms a lot of the floors of local quarries. The chalk rock, there's another one. Very important units. We can trace them across the whole of this area. They form part of what's called the Lewis nodular chalk. And if you go to, let's take it right the way to the other end. Let's go to Aston Rowant. You know the M40 going through there, and you can see the chalk strata going through. Well, when that was excavated, here's the chalk rock. There's the top rock. And those units are present across at Aston Rowant. We can track them across the whole area. In fact, they've been correlated. There's Aston Rowant, West Wickham, Missenden, Kensworth, Luton, right the way through. There's Reed, the quarry I showed you at the beginning. So you can see that these units can be tracked across the whole area. There's the chalk rock at the top of Baldock. And then what I can also pick out, and down the bottom here, you can see there's another dark line. There's another one here, and there's another one there. These are marl seams. These are discrete layers, maybe about a centimetre, 2 centimetres thick, of rich in clay. They're characteristic of what we call the new pit marley chalk. You know, it says what it does on the can, so to speak. You know, it's a marley chalk. We have marls in it. Many of these marls can be traced right the way across England, southern England, and in fact we can trace them across into Germany. And each of those marls can be individually fingerprinted on its chemistry because they were volcanic in origin. They landed as a layer of ash, a bit like the Icelandic ash cloud. Well, there was no Iceland, but we had ash clouds during the late Cretaceous because the Atlantic was opening, and the result was some of the beds in the marls that we see in the chalk. So there we go, there's two of what we call the new pit marls. And again, like I say, these units can be tracked right across England. This is down in Dorset. We have the Seaford chalk, the Lewis, the new pit, and you can see, these are petrophysical logs measuring resistivity in the grounds, below the ground surface, and we can correlate those units in individual marl seams across the whole area. So hopefully I've proved to you that even at Baldock we had this Lewis nodular chalk on top and the new pit marley chalk underneath. They're different, even in our own little area. And if we look at the Chiltern section, the Chilterns forms the northern arm, if you like, the northern rim of the London Basin. And we can track the chalk that we have here underneath the whole of London. It doesn't get any younger. That break, that 85 million year break, that erosion surface is present right underneath the middle of London. I know because we've looked at all the boreholes that Thames Water have been doing for the Thames Tideway, and we've dated the chalk right to the top, and it's exactly the same age that we see at the top of the Chilterns, or as we come down through the Chilterns in this area. So we know that we can track that same chalk across the whole area. And that's what it looks like, the typical white chalk. This is Codycock Quarry, just up towards Hitchin. So standard bit of white chalk, the Seaford chalk, that's the youngest chalk we see in the area. And that's sitting on top of the Lewis nodular and the new pit. So this is the one with all the flints in. It doesn't have the nodular hard ground, which the Lewis chalk does, and it doesn't have the marls, which the new pit does. But it has the flints. That flint's called the Seven Sisters flint. And if you know the Seven Sisters in Sussex, you can go and stand right below the cliffs at Seven Sisters. The big flint you can see a third of the way up the flint is exactly that same flint. We can track that flint right the way across southern England. When we look at the different formations, again, this was work that was done by Rory Mortimer back in the early 90s. We can characterise the different formations into their aquifer potential. The Seaford is a very high, it's one of the best aquifers we've got in southern England. You know, it really is good. And it does exist underneath the London Basin, so it's important that we protect it. The Lewis formation, it's mixed. it's very nodular. It's quite granular. In some places it can be very good. In other places it's not so good. It's better if it's fractured, but it's not always fractured. Whereas the new pit chalk, which has got the moles in, you think, okay, that's probably going to be the worst aquifer, but if it's fractured, we go from having a permeability which is very, very low, and it pushes it right up. One thing I should say that in the chalk, because of all those tiny coccoliths, the porosity we got is what we call microporosity. It's down to about, so we're seeing porosities of around about 44%. So almost half the rock is whole. But it's microporosity. It's difficult to get the water through it, but it acts as a fantastic filtering system. That's why your water is nice and clean when it comes out of the chalk, because it's been filtered through all those coccoliths. So just finishing off. I looked at the Misbourne several years ago now, just to try and see what the geology was affecting in the valley there. This is flowing over the New Pit Marley chalk. It's a nice flow here. Less than 400 metres downstream is that, and it should be there. This is over the Lewis chalk. As soon as the Misbourne, at this stage, this was about, Roger, when was it, 2010? When the Misbourne hit the Lewis chalk, it just disappeared. The geology was having its wicked way with the chalk stream. And the same thing happens, we know that, and obviously chalk streams, chalk bournes are very much affected by both the geology and the annual sort of seasonality of rainflow into the area. And we can see in this, if you, during the winter, you push the water table up, then springs will come up higher in the valley, whereas by comparison with a summer situation with the water tables down, then you'll perhaps pick up the perennial head, and you'll get the winter-born valley here. It's been affected by both the topography and obviously the weather conditions. And if you see that in action, here's the Bourne gutter flowing in March, sort of this year, sort of down through the lower part of the valley there. Year before, this is the same valley. Chalk streams come and go, but that's what they're supposed to do. It's a natural phenomenon. It's very nice to have streams flowing, but it's not always the case that they should. Any questions?